The quiz problem for today concerned a sand pile model, y equals 0.00130031 x cubed, where x is the diameter in centimeters and y is the volume in tablespoons. Oh, I take it back, we phrased the volume to be in liters, where x was the diameter in centimeters. And this might be a fairly realistic model. I actually tried to come up with a number that would correspond roughly to what you would get with real sand. Now, we say that what we're asking here is when x equals 30 centimeters, that is when the pile has a diameter of 30 centimeters, at what rate is the volume increasing? And then how much volume increase would correspond to a 0.1 centimeter increase in diameter? We first look at the rate of volume increase with respect to diameter. We know that that's the derivative of the volume function. The rate of y with respect to x. The rate of change of y with respect to x is the derivative of this function. And the derivative we find to be 0.0093x squared because, as we found out last time, the derivative of y equals ax cubed is 3a times x squared. If we take a equal to 0.0031, 3 times that's 0.0093, and that's how we get our y prime of x. So that at x equals 30 centimeters, at the diameter 30 centimeters, we find that y prime takes the value, well, y prime at 30 centimeters, we plug in 30 centimeters for x. That's what x stands for, the centimeters of diameter. And we get y prime equals 8.37 liters per centimeter. Now that's a little hard to read because I first wrote centimeters and then had to put the liters in above it because I wasn't thinking very clearly, but it's liters over centimeters. At the rate of 8.37 liters of what? Liters of volume change per centimeter of diameter change, what do we get? We see that the diameter change at the rate of 8.37 liters per centimeter of diameter, the diameter change corresponding to 1 centimeter, 0.1 centimeter, or a diameter change of 0.1 centimeter implies a delta y, a change in volume of 0.837 liters per centimeter times 0.1 centimeters, or 0.837 liters. Now it seems I've written 8.831, I really meant 0.837 liters there. So we see that by calculating the rate function, we can determine the rate at any given diameter, and then if we have a diameter change at that diameter, we can calculate the additional volume that will be required to achieve that diameter. Looking at the graph, we see a graph of volume in liters versus diameter in centimeters. And at 30 centimeters we have the volume of 83.7 liters, just plugging 30 into this function for x. And we have a tangent line at this point whose slope is y prime of 30, whose slope is therefore 8.37 liters per centimeter, as we found earlier. The approximation we've used essentially follows this tangent line along for 1/10 of a centimeter of diameter and uses that to determine the volume, as we're going to see in a minute.